Good evening, everyone. This is the Alabama A&M Senior Design Capstone team, and our team is called the Focus Force, and we're just thankful to be able to do this visual inspection senior design project. The agenda is today is something that was given throughout, where we will show our design process, so the background research, the technical approach, back of the envelope calculations such as FEA, final prototype design, and experimental testing and validation, and just the takeaways that we've learned.
So the overall scope of our project is to create a visual inspection system that will take pictures of different mechanical components, run those components through a program, and through that program it'll determine if there's any defects, and if there are any defects, it'll classify those different defects according to the type of defect it is. The need for this project is based off of in manufacturing environments, when components are going through inspection, they're more prone to human error. So with our project, we hope to create an automation process that speeds up that process and lowers the risk of mechanical errors or human errors.
So these was the components to be inspected, the 4 components that were given, and
So here we have our brainstorming. We brainstormed our overall concept generation design. So we have the data storage as a flash drive, and our IPU, our image processing unit, is a computer, where we are actually using a smartphone to take the picture through the microscope. So yeah. And here we have our background research. So we used a Arduino Uno R3 board to power our servos, and for the external power system, we used a Albronic 2200 battery.
As for the grasping mechanism, we have 3 different designs that we looked at and considered. So for the first one, we have a simple parallel jaw grasping mechanism that uses 2 gears and brings them both in together. And then for the second one, we have a 4-bar linkage design that's good for movement, but when it comes to mobility, it's a little bit heavier. And then for design 3, we have a system that keeps one of the arms in place, and the second arm is moved by 1 single gear. And then for our chosen concept, we decided to use something close to the 3rd design that we just showed, that utilizes the arm that stays in place and the one that moves along with this gear. And it's made out of PLA filament because it's lightweight. We didn't want to deal with too much heavy weight, so that way we could fit in the requirements. Yep.
So here we have our organizational structure of the team. We're divided into 2 subgroups, which is the mountain team, which is myself and Luke, where we handle the material selection and the overall system configuration. We also help do the modeling and simulation aspect of the design system under the specified conditions. And we also run some diagnostics of any issues that we have occurred. And then the other team, we have the defect analysis team, which is Kermit and Vanessa, who are responsible for the machine learning and data analysis aspect in MATLAB and Arduino. And they handle the software integration with the hardware, and also automates the analytical model building for the defect classification.
So these are just the functional requirements of the system, or what we're trying to build for. We have to have an image be capturable on at least 5 axes. The image capture does not require manual actuation by the operator. Continuous 360-degree rotational X and Y, Z translational capabilities. And parts should be firmly constrained without damaging parts or coatings. And then this is just kind of the functional requirements. The inspection process to be able to differentiate between different types of surface defects. And
So, for our overall concept generation for the programming, we decided to go with MATLAB. MATLAB has different built-in functions that can help process our code, so that's what we decided to use for our image analysis.
these are just some of the back envelope calculations that we conducted. So in this first slide, we knew that our rack was around 4.5 inches. And so we needed to know how we were going to design our spur gear. So we realized that, hey, we needed to have a diameter of 2.8 to linearly travel across the rack. In some of our FEA calculations, we had to calculate for torque for the spur gear. So we used the force that was created from the D shaft's mechanical properties, and then used the radius of the spur gear that was given. And then these are just the calculations for the spur gear itself. A lot of these calculations are from machine design terminology of a spur gear. For the diametral pitch is 8 and the number of teeth is 23. The pressure angle is 20 degrees. And so what we did was we created a spur gear and also a rack, but kept the diametral pitch the same so that the meshing would be fit together. This is some of the FEA analysis. As I talked earlier before, we talked about adding the torque, which was in the initial conditions. And then we added the force due to gravity on the parts where it would come in contact of the gripper. And then this is the total displacement and the von Mises stress. And just this was the allowable stress of where it got the highest. And the factor of safety came out to be 2.566.
And so for our final prototype design, we, as you can see, we have the batteries, the Arduino boards, and our actual grasping mechanism holding the coil. And for the testing procedure, we test the system's grasping mechanism with each component and ensure that the components were securely held, and we added a rubber material to the actual teeth so that way it wouldn't slip when holding things that are heavy or damage them when they're holding them. And then to program the system to rotate and tilt each component at various speeds and angles, record each movement, and use sensors or visual markers to confirm that the system achieves and holds the desired positions, and confirm that each image is automatically saved to the specified digital location.
Here are some of the videos of just the grasping mechanism to pick up each part. That is for the printed wiring board. Here's for the spring. And for the whirring gear. I'm now picking up the whirring gear. I'm now picking up the whirring gear. And this is just the grasping mechanism holding the D shaft. And this is the overall setup where each part will be taken to the camera so that it can be for the defect detection.
And in this setup, we do have the camera on a phone stand, but it's still able to be compatible with a stereo microscope.
This is the Arduino code, and so how the code works is there are 4 servos, and you attach it onto the digital PWM. And then how we control it is we use a serial monitor. So we input angles to tell it where to go. You see in the testing, we were able to move it up and down and rotate it and tilt it. That's how we control it in the Arduino code. And then each servo kind of works on a switch case. So we'll be able to tell, okay, servo 1 to move in this space and servo 2. It works in a switch case environment.
So here we have our automatic image capture. So right here, I had to use a Android debugging bridge by USB to establish an automatic image capture to prevent the operator from having to always manually actuate the image capture of the part. So here, this is just me in a command prompt programming that my device is registered in the PC and is able to establish a connection. Right here, I used a external app called Automate, where I'm able to establish a flow to where I can take the picture. It shows me that a picture was saved in my phone, and then I put in a 30-second delay to where the operator has time to actually analyze the part in MATLAB, and once it's time to move on to another picture, it'll be up and ready to take that next picture. And the last picture is just on phone screen showing how the process goes in script. And this first image is the MATLAB code used for actually pulling the images from the phone into MATLAB for image analysis. Yes, it establishes a continuous loop of automatic image capture, and it will later store that data that it gets from the MATLAB code to a flash drive for later use. And the bottom is just an example of how it shows up pulling the file from my phone to the MATLAB code.
Okay, so this is our MATLAB code that we developed for the defect detection. Pretty much after the picture is processed into the code, it'll convert the image to grayscale so that different features like lighting doesn't affect the sensitivity. So once it converts it to grayscale, a median filter is applied. We applied a 3x3 median filter. That's more so for pixelated images. It's able to capture images of a small enough size, but also not too big to where you can't see smaller defects. And so after that, we also developed an adaptive threshold so that it's able to view images of varying sizes, etc. Cool thing about MATLAB, which is also another reason why we chose MATLAB to process our code, they have an image processing toolbox that has default sizing and configurations that we were able to use for our different defects. So for things such as eccentricity and solidity, solidity refers to how complex a shape is. So if it's closer to 0, it's more filled in, so there's no holes. Whereas if it's closer to 1, you'll have more like rigidity, more deformation, stuff like that. And then as far as eccentricity, that refers to the elongation of the shape. So if it's closer to 1, it's more longer. So that would be more applied towards like your cracks, scratches, etc. We can go to the next slide. These are the different program outputs for the different components that we had. So if you look, well, can't see it, but it covers the area, it covers the eccentricity as well as the solidity. It also explains what type of defect is available, such as cracks, nicks, dents, scratches if they're there. We also set it up to where if there's other defects that we didn't specify that are in those images, it picks up on that as well. And then we also set it to where if there's no defects at all, it'll specify that there's no defects present. Go to the next slide. And then these are just pictures of the output. So these different boxes pretty much just show the different defects that are on the images. We increased the sensitivity to where it's able to pick up the slightest and the tiniest defects. So these circles pretty much just highlight the defects that are on the different components.
Here we have our financial statement. Pretty much we had a budget of $1,000 for project expenditures. We had to get 3 dual shafts U-mount servos with an additional 1 regular shaft servo motor. And we also needed a Arduino R3 board to power the servos. And we have a
Power distribution board.
Yeah, power distribution board. And also we needed the LiPo batteries. We got 2 just in case one went dead. Also we needed DuPont wires for the connections of the battery and servos. And of course the inspected parts, so the D-shaft, worm gear, spring, and power wiring. This totaled to $258.85. And of course we needed like other little purchases like fasteners and tooling to like fasten everything down.
Lessons learned. So one of the biggest like design considerations that we had to deal with was material selection. We realized that the D shaft was a very heavy component, and so the material that we went with was ABS. And although ABS is durable, it's brittle and it has a slippage, so we had to accommodate that by getting polyester felt so that it would be able to increase the friction so that components wouldn't fall. One of also the biggest things was we knew we needed a external power supply, because it's hard to power all 4 servos onto one Arduino board. So you need an extra power supply to be able to deliver the right amount of current to each servo. And then we also got a voltage, a UBEC, so that we wouldn't be overloading the current on one servo. And then testing and time management is one of the biggest things. Like you have to set out time, like a good testing schedule is one of the biggest things that we learned, is that, you know, to meet all requirements, you need a good setup, and that's just kind of something that we learned in our time. And yes. We just want to thank Sandia and Dr. Patrice and our professor, Dr. Drago, for just being patient with us and working with us and helping us grow as engineers in this CM Design project. We'll set this time for questions. Thank you, everyone.